Okay, welcome back, everybody. So, what I wanted to do today is continue on with more examples of undetermined coefficients. So I figured we would do at least like 2 more examples so that you've basically seen pretty much every configuration that can happen. Of course, as I said, there are some combinations of these parameters that would make the resulting computations be pretty nasty to do, would be pretty complicated, involve pretty long calculations. So, that's more okay for the style of assignments that you all are doing in this course, since everything is, non-synchronous. You're not sitting in a classroom having to take it, so you have a little bit more time. So having you do a little bit more involved computations is more okay for this setting. But even so, it's not going to be anything ridiculous. So typically, multiplicity plus degree will not be more than 2 or 3. Okay. So that's how it's going to be. So I wanted to do, like I said, next example of undetermined coefficient stuff. So let's just, let's find a general solution of the equation y double prime plus 9y is equal to 4 cosine of 3t. Okay. So, what do I do here? The first few steps are kind of always the same here. The idea is I write a characteristic polynomial first and foremost. Characteristic polynomial is what? Well, this is z squared plus 9 here. Okay, well, what are the roots of this thing? Well, it's got 2 roots, plus or minus 3i. Right. So roots of that polynomial are plus or minus 3i. Okay. So then what is the homogeneous general solution? Using these roots, homogeneous general solution is what? This is C1 e to the 0t, because the real part of this is 0, times cosine of 3t, plus C2 times e to the 0t sine of 3t. Alright, so that's simple enough. That's my homogeneous part. Okay, so then in order to be done, in order to have found general solution to this, I need to find the particular solution to this. In order to start that process, right, notice the f of t is 4 cosine of 3t. I have to do my usual thing and write, okay, what is the degree of this? Still degree 0 because this has no t showing up. What is the characteristic of this? Well, let's see here. So this right-hand side, it doesn't have an e to the anything showing up, so the real part of this must be 0. Plus I times 3, right? Because this, and you might say, well, wait, like, why is there not a sign showing up here if this characteristic is 3i or i3? Well, you could just take all of the b coefficients there to be 0, right? In this thing being in characteristic form, you can take all those b coefficients on that second polynomial to be 0, and that's what gives you this having characteristic 0 plus 3i. What's the multiplicity? Well, is 3i a root of the characteristic polynomial for this equation? Yes, it is. It's a root of multiplicity 1, right? Its complex roots comes in a conjugate pair. It's listed once here as multiplicity 1. So in this example, we still have 0 degree, but we have characteristic that is complex, so characteristics 3i, and the multiplicity is not 0, right? So it's slightly different than what we've seen before, but let's see how this works. So according to my recipe, I don't have that written down here, but according to my recipe, what should be my form of the particular solution? Since m is 1 and d is 0, remember that the t terms in this count down from m plus d, right, to m. Well, m plus d is 1, and m is 1, right? So what do I do here? Well, this tells me that I'm only going to have t terms showing up here, right? So the the particular solution here is going to be of the form a naught t times cosine of 3t plus b naught t sine of 3t. Okay. All right. So this is going to be my proper guess here. Again, note that there's no t showing up here, but a t shows up in my guess. So something like that has happened before in one of our previous solutions. Also, only cosine showing up here, but in this expression I have both cosine and sine. So it's very important that I follow this procedure, because if I don't follow it like this, I'm typically not going to be able to get the right answer out of this. Okay, so let's see what to do here. Now I'm going to be plugging this into here, so I have to compute its derivative and its second derivative, as usual. So what is y sub p prime? What is this? Unfortunately, I'm going to have to do product rules all over the place here. No avoiding that. So here I'm going to get a naught cosine of 3t plus a naught t times minus 3 sine of 3t. Right, plus b naught sine of 3t plus 3 b naught t cosine of 3t. Okay, so that's using product rule. So from this one I get these two terms, from the second term I get these two terms. Okay, let's compute the second derivative of this thing. So y sub p double prime. Well, the derivative of this term is just minus 3a naught sine of 3t. This term I'm going to have to use product rule. So I would get plus, or maybe I should say minus 3a naught sine of 3t minus 9 a naught t cosine of 3t plus 3 b naught cosine of 3t minus 9 b naught t sine of 3t. Let's clean that up just a little bit. Okay, so this would be minus 6 a naught sine of 3t minus 9 a naught t cosine of 3t plus 3b naught cosine of 3t minus 9b naught t sine of 3t. Okay. Let's see. I missed a term here. So, okay. So derivative of this is this. Derivative of this is these two terms. Derivative of this is 3b naught cosine 3t. Derivative of this is, I should get a plus 3b naught cosine of 3t. So this should be a 6. I should get an extra, so from the derivative of this, from this previous part, I should get a plus when I've taken the derivative of with respect to t of this t part. So this should be plus 3b naught cosine of 3t. So this should be a 6. Now that has a hope of being right. Okay. So that's a 6. If I change that to a 6, I think I'm good here. Okay, so this is a 6. All these others are negative. Yeah, okay. All right, so this is what yp double prime is. All right, so now I plug the particular solution into this differential equation here. All right, so let's do that. So what is y sub p double prime plus 9 y sub p? That should be equal to 4 cosine of 3t. Now, y sub p double prime we just computed to be minus 6 a naught sine of 3t plus, or minus 9 a naught t cosine of 3t plus 6 b naught cosine of 3t minus 9 b naught t sine of 3t. So all that is y sub p double prime plus 9 times y sub p. Remind yourself, there's what y sub p is. So this is plus 9 times a naught t cosine of 3t plus b naught t sine of 3t. And that has to be equal to 4 cosine of 3t. Okay. Now, I want you to pay attention to how nicely this works out yet again, right? So we saw this time and again yesterday, that this typically worked out to be really, really nice, and it wouldn't have worked out to be any other thing had I chosen a form for my particular solution y sub p that was changed in some way. So this is very, very strict in this choice, and that's why you just have to follow this method. There's no real wiggle room here. Okay, so 9 a naught t is going to cancel with minus 9 a naught t, or yeah, sorry, 9 a naught t cosine 3t is going to cancel with minus 9 a naught t cosine 3t in this term. 9 b naught t sine 3t cancels with minus 9 b naught t sine 3t here. Right. So what am I left with? Well, I'm left with minus 6 a naught sine of 3t plus 6 b naught cosine of 3t is equal to 4 cosine of 3t. If these are going to match up, right, then what does minus 6a naught have to be equal to? Well, there is no sine of 3t over here, so minus 6a naught has to be equal to 0. And 6b naught has to be equal to 4, since it's the coefficient on the cosine of 3t term. And so these are the equations that result. Now, the first equation implies, of course, that a naught is 0. The second equation implies that b naught is 2/3. Cool. Cool, cool, cool. All right. Very good. So, if we go back to our particular solution here, we found that a naught has to be 0 and b naught has to be 2/3. And so, this means that our particular solution, y sub p of t, must be 2/3 t sine of 3t. Right? Okay. And so, the general solution that we originally sought must be what? Well, as usual, this is homogeneous part plus particular solution. The homogeneous part we found to be c1 cosine 3t plus c2 sine 3t. And the particular solution we just found to be 2/3 t sine of 3t. All right. Okay. Let's do another example that illustrates what to do when we have a degree that is not just 0. So let's have a quick look here. So yeah, here's a great example. So find a general solution of the following. If you look at this example in the notes, there's a typo. But what I'm writing down is the correct one. So y double prime plus 2y prime plus 10y is equal to 4t e to the 2t. Okay? So, how do I find a general solution to this thing? Well, the process is the same as it always is. I first write out the characteristic polynomial. So what is it? Here it is z squared plus 2z plus 10. We've seen this one several times now. But remember, you can do this with several of these, right? This completing the square business to make this easy. Of course, if you don't like that, you can always just use the quadratic formula, right? If you don't want to waste a single second trying to come up with a nice way of expressing these roots without using quadratic formula, you can just use the quadratic formula. So, but we notice that this is just z plus 1 squared plus 9, or plus 3 squared. Right, and so this tells me that the roots are z equals minus 1 plus or minus 3i. Right. Okay, so there's my roots. Here is my right-hand side forcing function. Oh, maybe before I do that, I'll go ahead and write the homogeneous part. So what's the homogeneous part here? Well, based on these roots, this is c1 e to the minus t cosine of 3t plus c2 e to the minus t sine of 3t. Oh, I wanted to draw your attention to something in the previous example real quick. So, in the previous example, of course, we've seen an example of this before, so this isn't brand new stuff. But in the previous example, uh, on the right-hand side we have 4 cosine of 3t, but the particular solution we end up with is not really, it doesn't even involve a cosine, right? It involves a sine. So, and of course it involves a t, whereas the right-hand side thing doesn't. So remember that while the motivation for doing undetermined coefficients was that we were selecting a form for the particular solution that transformed to something that was similar, it doesn't actually need to be, superficially, right, it may not look that close, right? So 2/3 t sine of 3t doesn't look that close maybe to 4 cosine of 3t, but it turns out that's exactly what you need for that problem. Okay, so anyway, this is my homogeneous part for this equation. All right, so then my right-hand side forcing function is 4t e to the 2t. Okay, so now what do I do? Well, I write out the 3 quantities I'm always interested in. First one is degree. Aha! For the first time ever, right, in these examples, I get to write that the degree is something other than 0. What's the degree? Well, the largest power of t showing up here is 1. Right? What's the characteristic mu plus I nu? Well, there's no cosine and sine showing up, so nu is 0. All right, since there's no cosine nor sine. So then my characteristic is going to be 2 plus I times 0. Right? So just 2. And that's coming from this term. Alright, what about the multiplicity? Well, is 2 a root of this characteristic polynomial? No, the only roots are minus 1 plus minus 3i, right? So the multiplicity is 0 because it's just simply not a root. So what do those 3 quantities tell me about what the particular solution should look like? Remember, the t terms, the polynomial terms, count down from m plus d to m. For us, here, m plus d is 1, and m is 0. So they count down from t to the first to t to the 0, to the constant term. What does that mean? Well, in this case, here's my characteristic. What does this thing look like? Well, it looks like a naught t plus a1 times e to the 2t. Right. Again, it counts down from the t term to the t to the 0 term. Okay. And so this is what I get. I don't get any b terms because, well, the characteristic is just real, right? It's just 2 plus I times 0, so I don't have that other part. Okay. So that's the form that it should take. Now let's do what I always want to do. I want to take derivatives of this and plug it into this relationship and actually solve for the a0 and a1. So y sub p prime of t is what? Well, let's do this by product rule here. So I have a thing in t times e to the 2t. So the derivative of this thing, of course, is a0, right, times e to the 2t plus a0 t plus a1 times 2e to the 2t. All right, so this is what I get for my first derivative. For my second derivative, what do I get? Okay, so for this term, I would get 2a0 e to the 2t. For this term, I am going to use product rule again, so I'm going to get plus a0 times 2e to the 2t. So I'm just going to go ahead and write that as 2a0 e to the 2t plus, when I don't take the derivative of this first part, and then I take the derivative of the second part, I get 2 e to the 2t again there. So maybe let me simplify this a little bit. So this is 4 a naught e to the 2t plus 4 times a naught t plus a1 times e to the 2t. There we go. Okay. All right. Let's plug this into the differential equation. All right, and solve for these two undetermined coefficients. So the differential equation for the particular solution will be y sub p double prime plus 2 y sub p prime plus 10 y sub p, and this is equal to 4t, or it should be equal to 4t e to the 2t. Okay. Let's just plug these things in. So y sub p double prime we just found to be 4 a naught e to the 2t plus 4 times a naught t plus a1 times e to the 2t. That's y sub p double prime. Plus 2 times y sub p prime, which is a naught e to the 2t plus 2 a naught t plus a1 times e to the 2t. Okay. Plus 10 times y sub p, which is a naught t plus a1 e to the 2t. Okay, and all that has to be equal to 4t e to the 2t. So I'm going to need to group these things and make sure that I set the proper things equal to one another. Okay. So let's be careful here. So first of all, let's group everything that doesn't have a t in it together, or let's try to do that in a nice way. So we have 4 a naught e to the 2t plus, maybe I'll just write out all this, so times 4 a naught t e to the 2t plus 4 a1 e to the 2t plus 2 a naught e to the 2t plus 4 a naught t e to the 2t plus 4 a1 e to the 2t plus 10 a naught t e to the 2t plus 10 a1 e to the 2t. And all that is equal to 4t e to the 2t. Okay. So let's group everything with or without a t and then with a t. So without a t, what do we have? We have 4a naught. So that takes care of that. And then we have plus 4a1. That takes care of this term. Plus 2a naught. That takes care of that term. Plus 4a1. Takes care of this term. Plus 10a1. And all of that is times e to the 2t. Right? Plus something times the t e to the 2t. So this is 4a naught. That takes care of that term. Plus 4a naught. That takes care of this term. Plus 10 a naught. And that's times t e to the 2t. So every term is accounted for here. And all this is equal to 4t e to the 2t. Well, once I simplify these slightly, so let's go ahead and do that. 4a naught plus 2a naught plus 10. Oh, there's no other a naught here. So this is 6a naught plus 4a1 plus 4a1 plus 10a1 is 18a1 times e to the 2t. Plus this is 18a naught t e to the 2t. And this is equal to 4t e to the 2t. Since on the right-hand side there's only a t e to the 2t, this first expression must be 0, and the second expression must be 4. So 6a naught plus 18a1 must be equal to 0, because there is no just purely e to the t term over here. And 18a naught has to be equal to 4. And so these are the relationships you get. Well, 18a naught being equal to 4, that implies that a naught is 4/18 or 2/9. Okay. Well, if a naught is 2/9, then the second expression implies we have 6 times 2/9 plus 18 times a1 is equal to 0. What does that mean? So I've got 12/9, or maybe I have here like 18. So 18a1 is equal to minus 12/9. Right? So what is that? Well, that's 3 times 4. This is 3 times 3. So this is minus 4/3, if you like. Okay. If I divide by 18, a1 is equal to minus 4/3 times 1 over 18. So this is 2 times 2. This is 2 times 9. So this is a minus 2 over 3 times 9, which is 27. This is minus 2 over 27. And thus, our particular solution, y sub p of t, is, remember this was a naught t plus a1 e to the minus 2t, or e to the 2t, sorry. It's this thing. So this would be 2/9 t minus 2 over 27 times e to the 2t. This is our particular solution. And thus, to answer that original question, the general solution is y of t, which is homogeneous part, plus particular solution. So this is c1 e to the minus t cosine of 3t plus c2 e to the minus t sine of 3t plus this particular solution we just found, which is 2/9 t minus 2 over 27 times e to the 2t. Okay. So that is how that works. All right. So now you have seen a smattering of examples that kind of shows you pretty much everything you can expect to be thrown at you from the undetermined coefficients side of things. Okay. So that's a pretty... So this concludes a decent array of undetermined coefficients problems. Undetermined coefficients examples. Okay, so so I encourage you to have a look at those. Now, let's start on the other thing, which, as I've said before, is used for the exact same sorts of problems. Um, you are not going to be told typically to do one or the other. Okay, so typically you will be just told to find a general solution, and it doesn't matter which one you use. For the purposes of practice, I'm going to post one homework tonight, probably that will be due before your exam. It will be fairly short. It will just be two problems. One will be undetermined coefficients. The other will be key identities. And that is kind of the only time when I would specifically tell you to use one or the other. In general, like on an exam, or future homeworks or whatever, you'd be allowed to use whatever method you want. So I want to talk now about key identities, and I'm going to cut this a little bit short because it turns out that I'm gonna stop the lecture a little bit early today because I have an appointment, but we'll pick up exactly here tomorrow. But anyway, how does this key identities business work? So before I can get into key identities, some review of complex stuff. Okay, and if any of this is confusing, I would encourage you having a look at like some basics of the complex plane, basics of the algebra of complex numbers. We're not going to get into it too deeply here. We're just going to do the bare minimum kind of that we need to do. So let's see what any of this stuff, or kind of what is needed here. So some review of complex stuff. So a complex number looks like this, where both x and y are real numbers, right? So both x and y are real numbers. A complex number is x plus iy. Now you've seen at this point, or hopefully you've seen, that a complex number really can just be thought of as an ordered pair. So if you have the ordered pair xy in the plane, that's really identical algebraically to the object x plus iy. Okay. So complex numbers can be thought of as just points in the plane. All right. Now, there's a couple of quantities associated with this complex number. There's what's called the real part of the complex number. All it is this thing. It's x. That's what's called the real part. I've already been using that terminology now, but now we're going to make it rigorous. There's also the imaginary part of a complex number. That's y. It's not y times I, it's just y. Okay, but notice that both the real and the imaginary part of a complex number are both real numbers. That's important. Okay, so even the imaginary part of a complex number is a real number. Okay, right? It's just the real number that multiplies the I in this. This is called Cartesian form, okay, or rectangular form of a complex number. Now, thinking of a complex number in terms of the plane, there's some geometric data, right, that I can consider. So for instance, I could consider the distance from this point to the origin. What is that distance? Using the distance formula, what is that distance? Well, by the distance formula, the distance from any point to the origin is, well, whether you want to think about it, it's the distance formula or the Pythagorean theorem. This is the square root of x squared plus y squared, right? That is my distance. Well, I have a special name for this. This is called the modulus of z. So the modulus of z is square root of x squared plus y squared. Okay, and what this is just the distance from the point, or the complex number thought of as a point in the plane, to the origin. Okay. Now, sometimes, of course, this radical is nasty to deal with, so sometimes you won't deal with this thing exactly, you'll deal with its square. So if I square both sides, of course, this is what I get. Okay. All right. So this is called the modulus of a complex number. Okay. So that's that. All right. So what else do I need to understand? Well, there's some basic things to understand here. So for instance, if I have a complex number z bar, as we've already seen, is x minus iy. Okay. If I take a complex number z, any complex number, and I multiply it by its conjugate, that's x plus iy times x minus iy. Right? If I multiply this out, the mixed terms cancel, and I just get x squared minus I squared y squared, right? But I squared is minus 1. Sorry. There, I squared is minus 1. So this is minus minus 1, y squared. So this is actually x squared plus y squared. But x squared plus y squared is the modulus squared. So if you take a complex number and multiply it by its conjugate, you get the modulus squared. Let's write that again. So z times z bar is equal to the modulus of z squared. If I divide both sides by the modulus of z squared, because modulus of z squared is x squared plus y squared. What kind of thing is that? X is real, y is real. So this is real. This is a real number. It better be, because this is the distance from the origin to that point, which, you know, we don't talk about a distance being a complex number. That doesn't make any sense. So this is a real number. So I can divide by it, right, so long as it's not 0. Well, the only time it's going to be 0 is when this is the origin. So let's just say we're not talking about that. So if this is any other point other than the origin, this distance is going to be positive, a positive real number. Let's divide by it. So then this means z times z bar divided by the modulus of z squared is equal to 1. This tells you something. It tells you that if you take a complex number z and you multiply it by its conjugate divided by its modulus squared, you get 1. What that tells you is that this thing in the parentheses here is the inverse of z, the multiplicative inverse of z. So if you have a complex number, z, which is x plus iy, if you want to find 1 over z, right, it's not as simple as just writing 1 over x plus iy. What is that? I have no idea, right? Well, what that is, it turns out, is x minus iy divided by x squared plus y squared. Or it's the complex number x over x squared plus y squared minus I times y over x squared plus y squared. What I've just showed you is how to divide by a complex number. You might say, why would I need to know how to divide by a complex number if we're solving differential equations, and differential equations, the output is always a real thing, right? Yeah, we know that complex numbers show up in computing the roots of these polynomials, right? The roots of characteristic polynomials, but why would I need to compute, why would I need to know how to divide by a complex number? You'll see why, okay? You'll see. So, One more thing before I move on. Complex number, written like this. This is rectangular form or Cartesian form. This is typically the form you think of a complex number as being in. It is perfectly fine to do all the algebra you want to do, but it doesn't behave as well with products, or I should say exponents specifically. So if I wanted to do something like, I don't know, say square root of 2 over 2 plus I square root of 2 over 2 raised to the 32nd power, right? How would I do that? That would be pretty annoying to do, brute force, because think about it. I would write this thing out 32 times. And I would distribute that, right? And so I would do it like a pair by pair, foiling if you if you like, right? I would do this pair by pair, like foiling this thing out. It would be a real nightmare, okay? So it turns out that there is a better form for this kind of thing, and it's called polar form. And the reason it's called polar form is because it's really just polar coordinates. Okay, so this is polar form for a complex number. To put a complex number into polar form, R is simply the modulus of z, or the square root of x squared plus y squared. Well, you've seen that before. That's saying that r squared is equal to x squared plus y squared. That is exactly what r satisfies in polar coordinates. And theta satisfies that tan theta is equal to y over x. This is just polar coordinates. Okay, this is just polar coordinates. So if you take the rectangular ordered pair xy and put it into polar coordinates r theta, this r and this theta written in this way are the same thing. Now, you're going to maybe complain a little bit. Okay, you're maybe going to complain ever so slightly. Like, what does this mean to raise e to a complex number, e to the I theta? What does that mean? Well, I'll show you. So, what is e to the I theta? E to the I theta is cosine of theta plus I sine of theta. So e to the I theta is the complex number that is in Cartesian form that has cosine theta as its real part and sine theta as its imaginary part. So another way of writing that is the real part of e to the I theta is cosine theta, and the imaginary part of e to the I theta is sine theta. You may have seen a result of this, okay? If I plug in pi, e to the I pi is cosine of pi plus I sine of pi. Well, cosine of pi is minus 1 and sine of pi is 0. So this gives me e to the I pi is equal to minus 1, or e to the I pi plus 1 is equal to 0. This is sometimes called Euler's formula. And, everybody likes it because it's a single formula that relates e, I, pi, 1, and 0. Right? So, relates 5 very important constants in math in a single relationship. So there it is. Okay. Now, you might say, where did this come from? I'm not going to do the full derivation, but if you want to know, power series expansions or Taylor series expansions for e to the x, cosine x, and sine x. Just formally write out the power series for these three things. Plug in I theta here, and do some algebraic manipulation, you will see that it splits it into half, into two pieces, right? Using the fact that I is just I squared is minus 1, I cubed is minus I, and I to the fourth is 1. And this loops, right? I to the fifth is I, and so on. Now it loops. So I minus 1 minus I 1, and that pattern continues. Once you see that, what happens is this gets sorted into a half. One half's an alternating sum that turns out to be cosine. The other half is I times an alternating sum that turns out to be sine. Cosine has the even terms, sine has the odd terms. Okay, we know that because cosine is an even function and sine's an odd function. Okay, so anyway, that's where this comes from. You can just prove it directly from the power series. So this is why this works out this way. Now, I'm going to stop here, but this is the starting point to understand the key identity stuff. Okay, so you have to know this stuff, or the key identities algebra is not going to make any sense to you. So anyway, we'll stop there, and we'll talk about key identity stuff some more starting tomorrow. So I will see you then.